class, we're now in chapter 12.4, and we're going to be dealing with evaporation and condensation. So evaporation and condensation, thermal energy, and thermal energy is heat flow. So the energy as heat. The rate of vaporization increases with the following: increasing surface area. So the more area there is, so if you think about, if you spill something out on a table and it spreads out, that is increasing the surface area. So more in contact with the environment, and the water will evaporate faster than something that's sitting in like a large bowl of water. Increasing the temperature. If it's hot, that water tends to evaporate faster than when it's cold. Decreasing the strength of intermolecular forces. So depending on what type of solution we're dealing with, if it's something that can is volatile very easy, it evaporates very easy, it's volatile, and that means that the intermolecular forces are not as strong with it as they are with something that's not as strong with intermolecular forces. So something that has a decrease in strength of intermolecular forces means that it's not holding onto those molecules to each other. So think of holding hands. They can let go very easily, and that will allow it to evaporate faster. Something that's volatile could be acetone, ethanol, things, gasoline. You know, these things evaporate very easily. They are volatile. If you leave that top open and you come back, that bottle will most likely be empty compared to something that's not volatile like oil. So evaporation, molecules on the surface of the liquid are held less tightly because they're not completely surrounded by other water molecules. So the ones at the top are missing molecules at this top layer. So even though the molecules below it pull them down, they're missing that full contact with our molecules. And if they are given enough in energy, they can escape from the surface and turn into a gaseous state. So that's what the evaporation is. So it's evaporation or vaporization. It is a substance that's converted from a liquid state into a gas state. So water, being in a liquid state, will evaporate into a gaseous state, which is water vapor or water steam, however you want to talk about that. Now, at a given temperature, a sample of molecules or atoms have a distribution of kinetic energy. So what does this mean? It means that these molecules are moving, and they're moving, some are moving faster than others. They are still attached, but they have freedom to move. And we look at the average of that kinetic energy. So think of that as the average energy that's allowing them to move. But the average simply means that we have some that are higher and some that are lower. Now, and that's what this distribution is. It's showing you. So only a small fraction of molecules have enough energy to escape. Those molecules that are high in energy have enough energy to escape the surface and evaporate away. Majority of them do not. We have to have something to allow that to happen, or they have to finally reach the surface or increase in kinetic energy. So if you look here, this is the fraction of molecules. Majority of the fraction of molecules, if you think about molecules in a container of water, for instance, majority of them are low temperature. And because they're low temperature, they don't have enough energy to move and break through the surface to evaporate away. There are others that are higher in energy, but the fraction, this is fraction of molecules again, they are not as many as the lower temperature. And then even though they're higher, there's molecules that are higher temperature and the energy is increasing, because if we go this way, it's increasing. There's still not enough of them to break the barrier that they have to have that minimum energy in order to escape the surface. There's very few that actually can break the surface. So this is a fraction of the molecules that have enough energy to escape, to become vaporized. Okay, so condensation, fancy word, condensed, think of it that way, is a physical change in which a substance is converted from a gaseous state to a liquid state. So this is going backwards. It is going from vapor into liquid. So if you think of steam, water, water vapor, it is now going back into a liquid state. You'll start seeing drops form. Evaporation and condensation are opposite. So evaporation is a liquid turning into a gas. And so when you boil water, and condensation is a gas turning into a liquid. And this is when it gets cold, you can start seeing water start forming on stuff. At the point where the rates of condensation and evaporation become equal, there's a fancy word called dynamic equilibrium is reached. What this means is that you have there's a rate of molecules that are evaporating, and there's a rate of molecules that are condensing. And eventually, the rates are the same. The rate that molecules are evaporating will match the rate of the condensation. So think of it as one person walks out, one person walks in, one person walks out, one person walks in, and it never stops. It keeps staying in this equilibrium. So think of a water bottle, and you put the cap on it, but you did drink some of this water bottle, and then you leave it for a few days. What you'll see is you'll see this water droplets are surrounding the top of it, but you didn't throw the water bottle, it didn't tip over. So where are all these water droplets coming from the top? That is dynamic equilibrium. You cannot see what's actually happening, but there is a rate of molecules that are evaporating still, and there's a rate of condensation that's happening. So think about it this way. We have water in a closed container. Water molecules will start evaporating from it, and that's because there's few gaseous water molecules in the space above the water. Then eventually there will be enough buildup, and that's that vapor pressure that is above the surface of the water. There will be enough of those water molecules that they will actually start going back into the liquid phase. And that is the equilibrium. There's a rate of water molecules going back into the liquid phase, and there are water molecules escaping the water and going into the gaseous state right above it, even though we can't see that. It's there. Those water droplets are telling you that there's something going on there. So here's a picture. So evaporation begins to occur. There's not very many water molecules above this. So this will happen very, there's nothing preventing this from happening. But see, this gets crowded over here. So these water molecules, the ones that have enough energy to break the surface, will start evaporating, and we'll have gas molecules, water vapor molecules above it. And that's eventually where you'll start seeing that buildup of water on the surface. Then eventually there'll be so many that they'll start going back into the water itself, and that's what the dynamic equilibrium is the rate of evaporation equals the rate of condensation, and this will stay continuous. It will not stop until something breaks that equilibrium, that rate. So vapor pressure is the pressure that vapor pressure increases with the following: increasing temperature and decreasing the strength of intermolecular forces. So if we were to start heating this up, we would have more molecules, or if it's just on a hot day, you will have more molecules evaporating away and going to above. So increasing the vapor pressure that's above it, the water pressure that's there, and decreasing the strength of intermolecular forces. So if you have something that by decreasing, that means they're not so strong, they're not holding on to each other, and it's easier to leave that surface. So vapor pressure is independent of surface area because an increase in surface area at equilibrium equally affects the rate of evaporation and rate of condensation. So when we look at vapor pressure, we're interested in the temperature. So if you remember going back to gases, vapor pressure, we would have to look up a temperature for the vapor pressure of water to remove that vapor pressure if we were doing a reaction in water. So boiling, during boiling, thermal energy, this is the heat flow, is enough to cause water molecules in the interior of the liquid to become gaseous. That's where you see the bubbles. They are changing into a gaseous state. They are still water though, so this is just a physical change. There's not a chemical change. The water is still water regardless of it being liquid or in a gaseous state. Once the boiling point of a liquid is reached, additional heating only causes more rapid boiling. It does not raise the temperature of the liquid above its boiling point, and I'll explain what this means. A mixture of boiling water and steam will always have a temperature of 100 degrees Celsius at 1 atm. Only after all the water has been converted to steam can the temperature of the steam rise. So what does that mean? I'm going to show you. It's saying that, it's stating, let's say we want to boil water. Water boils at 100 degrees, but you see this plateau? We are constantly adding more energy, and there will be a certain amount of energy that will cause the temperature to increase. So let's say we start here at 20, we get to 100. We start adding more and more heat, but something interesting happens is that it plateaus. No matter how much heat we add to it, the temperature doesn't ever go up past 100. Why is that? That's because it's an equilibrium here. It's a change of state. So this is a change of temperature. This is a change of state. What we had as a liquid is now changing into a gaseous state. So that's what's happening. That energy is no longer going into increasing the temperature. That energy is going into breaking bonds so that this can go into a different state. So it's no longer going into, gaseous state is the attraction to each other, intermolecular forces are no longer as strong. So the energy is breaking those attractive forces, and the water is changing from liquid to gas. And that's what's happening. And what it says, if you look back at the steam, the water so that's where we have a mixture of water and steam. And once all the liquid water is gone, then the temperature will start rising again. This also goes with cooling. We'll cover that in cooling. Temperature of water, if you have water, ice and water, that temperature will not change until that ice cube is gone. Once it hits well, I'll cover that. That's the next section. I don't want to ruin the fun. So that's what's happening. This is a plateau, is what you see here, and this is where it is changing from liquid to steam, and so you have a mixture until you have no more liquid water, then it goes back up. Okay, so evaporation is an endothermic process. When a liquid is converted into a gas, it absorbs heat. So it has to take in that heat because it needs that energy to break the molecules away from the rest of the liquid. That's what's happening at the plateau. Our bodies also use an endothermic nature of evaporation for cooling. That's because when we sweat, the sweat pulls that heat away from our skin, even though it doesn't always feel like it. And so overheating, for instance, causing our skin to be covered with liquid water. That water evaporates and it absorbs the heat, which cools us down. Problem is, if you're in high humidity areas, that doesn't really happen because it can't prevent the cooling. When the air already contains high amounts of water vapor, the sweat really does not evaporate away. Condensation is the opposite. It's an exothermic. Heat is released when gas condenses to a liquid. It has to, so it's higher in energy as a vapor, and then as it goes into a liquid, it has to release that extra energy in order to go into a liquid. So as steam condenses to a liquid on your skin, it releases heat. So you will have a far worse severe burn from steam than you will from liquid water. And that's because the amount of energy that is released from steam is far greater value than what is in liquid water. The exothermic nature of condensation is also the reason why winter overnight temperatures in coastal cities, they have water vapor in the air. And deserts do not have that same water vapor, so that's why it's colder in deserts than it is actually by the water, because the water can retain, it can release that heat as it gets cold at night, and it condenses back the water vapor into a liquid, and that's what keeps these coastal cities a lot better temperature than what you have in the desert. As the air temperature in coastal cities drops, the water condenses out of the air, releasing that heat. It doesn't always feel like it because it feels cold at the ocean, at the beach, but believe me, if that wasn't there, if you go into the desert, it's far colder in the desert than it is at the beach. So this little moisture, when water condenses, it releases that heat and it prevents the temperature from dropping any further. In deserts, there's a little moisture, so the temperature drops far more. So now we're going to look at heat of vaporization. The amount of heat required to vaporize 1 mole of heat is the heat of vaporization. So we're, of course, going to do some calculations. The heat of vaporization, so heat of vaporization is evaporation away at 100 degrees Celsius. And that is 40.7 kilojoules per mole. Excuse me, the change in heat of vaporization is positive because vaporization is endothermic. Energy must be added to the water to vaporize it into steam. The same amount of heat is involved when the 1 mole of gas condenses, but the heat is emitted rather than absorbed. So the change in, that should be a capital H, of vaporization is negative because condensation is exothermic, but it's still 40.7. So to show you that's what this is. If we look at it one way as vaporization, it's a positive because that's an endothermic reaction. But if we're going back from a vapor to condensation, same value, but it's negative. So we go from a gas to a liquid, and that is exothermic because it has to release heat. Okay, so here are some values for heat of vaporization, our normal boiling points, and you can see the amounts that are in kilojoules per mole for water, alcohol, acetone, and so forth. We use these to calculate how much heat is required to vaporize a given amount of liquid. So if we have a certain amount of liquid, we need to know how much heat it's going to take to vaporize it away. And we can also use this as a conversion factor. So this is in your book. Calculate the amount of heat required to vaporize 25 grams of heat at its boiling point. So there's no change in temperature here because this is at a plateau. This is going from a change of state. So if we look back and you see here, we are looking at something that is here because there's no temperature really involved because it's at 100 degrees Celsius. This is where we're adding energy, and there's a temperature change, which I'll show you what that one is. So in this case, we're given 25 grams, and we know what the molar mass of that is. We need to find the kilojoule. So we're going to use this conversion, this kilojoules of over moles, to determine how much heat is required to vaporize is 25 grams of water at boiling point, which is 100 degrees. But we're not interested in temperature because this is at a plateau. We just need to know when. So we're going to pull all our information, and here you can see this information that we are going to use these relationships. These are our stepping stones that are going to tell us how to do this. So we have our 25 grams. There should be a G there. We use our molar mass. That's going to cancel out. That's going to cancel out. 1 mole. And we have 40.7 kilojoules per mole. So this tells me that it's for 25 grams of water, it's going to take 56.5 kilojoules in order to heat that amount or vaporize that amount. Okay, so I hate that this happens. Okay, calculate the amount of water in grams that can be vaporized at boiling point with 155 kilojoules of heat. So this is opposite. We want to know the amount that is going to use this 155 kilojoules of heat. So what do we have? We're given the heat, and we need to find the mass. So we're going to work backwards in this case, where we were working forward, and this one we're working actually backwards. And this is kilojoules, so we're going to go from kilojoules. We're going to use the same conversion, but the units are going to be flipped. We're going to get the moles, and then we're going to use the molar mass. So in this one, here we go. We set up the 155 kilojoules. We use our conversion, the moles, molar mass, and that's going to tell us that it's 68.6 grams. And this is just telling you to have an idea of the magnitude. Does it look right? You should have some understanding, and that's what it's saying here. 155 kilojoules should vaporize close to 4 moles of water, which is consistent with the answer. 4 moles of water has a mass of about 72 grams. So it's just kind of giving you an idea of how to look at this. Okay, so here's a heating curve. And as you can see, the temperature increases, and that's the water. This is just I already showed you this slide, but we're going to do a problem where now we're going to combine what we just calculated here, what I just showed you here, with a calculation here. Because things don't usually stay at a plateau. We might start all the way down here, and we'll have to use a calculation for this and use a calculation for this, add them together to determine the full value of what's taking place. So again, the temperature of water as it's heated will increase till it gets to the boiling point, and then it'll stay the same until every last water molecule is changed to steam, and then it'll start increasing again. So here's another picture from another one of my slides. It just gives you more of a visual of what's going on. All right, so a plateau on a heating curve represents, I'm just going to cheat on these, and this is a constant temperature change and a change of state. So this plateau is a constant temperature and a change of state. And a slope line on the heating curve represents a temperature change. So that's what this represents right here. All right, so we're going to use a formula. And this formula, I just put these here so you're you're understanding what we're talking about here. This is a formula that's going to help. We just completed one that would help here, but I'm showing you now one that's going to go here. This is the heat equals mass times temperature change times specific heat. Now we're back to specific heat of a value. Okay, so best way is just to do a problem. Calculate the total heat in joules needed to convert 15 grams of liquid ethanol at 25 degrees Celsius to a gas at its boiling point. Ethanol has a specific heat, which is given to us, and a heat of vaporization. So we have everything we need to do for this problem. So I've broken up this into what's given, what's needed, and how we need to connect. So first things we need to understand, we have 15 grams of ethanol, and we start at 25 degrees Celsius. The boiling point is 78, and then it's going to be vaporized. So if we look at something like this, what it means is that we start here, we're going to this point, and then eventually we're going to have to deal with this because it's going to vaporize away. So we need to figure out the energy that's being used here with the temperature change, and then the energy to get it into a vapor. So that's what this is, even though it's not showing. So we're going to pull out all the information that we're given regarding conversion factors, because we're going to need to know that. We're going to need to know the difference in temperature, and then we're going to need to know the change, the energy used to change the state. So that's the total heat. We'll be adding these together. First, we need to calculate the temperature change, which is 53 degrees Celsius, and we're using this one for the increase here. So that's what we're going to use right here. So we plug this in, and it gives us 15 grams times the change in temperature plus the specific heat value, and that's what we have. So we have 3 sig figs, 3 sig figs, and exact. And this gives us a total of 1960 joules. But we're not done. Remember, we just calculated this first portion. We now need to do the second one, which I've already showed you in some problems. And so here, we're going to calculate that. So we take the 15 grams times the heat of vaporization, the grams cancel out, and it ends up with 12,600 joules. We're going to add those together, and this gives us 14,600 joules for those, the increase in the heating curve and then the plateau. This is the total for that.